Alright, today, here's what we're doing. I'm going to try to give you some time today where you can work on that assignment. You had page 216, that's due Monday. Keep that in mind, I'm going to try to give you some time today to work on it. Probably not as much time as I did yesterday, but today I definitely want to have a chance where you can actually start, you can actually get through that, you can ask any questions, because I know like some of that can be challenging, especially if you don't know what it means when there's a fraction on the inside or a negative, or when they mix multiple ones together, like little things that you forget you're supposed to do first. The order of operations are behind you, so you can see that on the board: horizontal shifting, stretching, shrinking, and then you go to your reflections and you do vertical shifting. So make sure you go in that order. It's the order of operations. Okay, what we're doing today is we're still graphing, but we're doing a completely different animal today. Like, I've been teaching you the rules for very generic ways to look at a problem and graph it. Like just, dragging things around when the picture's already provided for you, or the function's provided and you're going to just manipulate it a little bit. What we're looking at today is how do you draw for the first time a polynomial? Like something that actually has curves to it, and what's the process, like what's the thought process that I go through to actually solve this thing? I'm going to look at maybe two or three examples of different ranges, and then what we're going to do is hopefully by the time we're done, we'll go into your Chromebook and we'll see, are we at least accurate? Or does it look somewhat correct? Does that make sense? And I'll show you the level of difficulty we need to be at by the time you hit calculus. So today is the first attempt at doing this. So this is something we're going to extend throughout the kind of the semester and the year, but today is where you get basically all the rules that you need. But then we just learn little steps, like little things here and there that help you to do further. Okay, so first, I know this is going to seem weird. We're jumping to like section 2-3. I said we can bounce around a little bit in this chapter because I want to go in an order that makes sense to you. So like the first section of chapter 2 was section 1-6. I know that's kind of weird, but that's where we graph. We start, moving things around and doing transformations. This section, we learn the rules for if you don't have the graph provided, how can you get to it? And so there's little things we're going to have. So we're graphing polynomials. So these are the little things. When I look at a problem, an equation, or an expression, I can kind of see where that thing is going, how it's supposed to flow throughout the whole entire graph, without having to type really anything in, because there's little like telltale signs of what you look for. Okay, and so we'll kind of learn the basic rules and kind of show you what I'm talking about as we go. So here's the rules. I'm going to write them down. Number 1, it's called a leading coefficient test. Coefficient test. It's one of the easiest things in the world. A leading coefficient, that word coefficient is the number that's in front of your variables, right? So if I were to give you a function, something like this, 2x squared plus 8x plus 6. Okay? I already give you something like that. That's a polynomial, right? It's a trinomial, but it's a polynomial of some type. What's the leading number in front of the highest degree item? 2. What I look for, instead of just noticing that it's a 2, I look for if it's positive or negative. That's the important thing that I look for. That's the coefficient test. So if your number out front, the highest degree term, so maybe I'll put this, I'm looking at the highest degree term. So if you need to rearrange your polynomials so the highest degree is in the front, fine, so be it. But if your term is positive out front, if your term is positive, you have a normal graph. So I know that seems a little weird for me to say that. You have a normal graph. So this is something you're going to have to learn, like the generic looks of what polynomials are. So what I mean by normal is that on a graph, certain graphs like go up, certain graphs go down, some graphs go like opposite. And we'll learn that as we go through this section and the next section. This will be a normal looking graph. We're not going to manipulate it in some way. It's not flipped over. That's what I'm talking about. It's not inverted where it's like a reflection. That's what I'm looking at. If the number is negative, it's a reflection across the x-axis. And that's the type of problems you're doing right now in the homework. So if there's a negative outside, this graph would be flipped from where it originally is drawn. But again, it goes across this axis. So if this picture's up here, now it's down here, and it looks the opposite. So that's what I look at. I know it's a simple little rule. It's something I look for. Okay? Next, we look for end behavior. This is the hardest thing to explain, especially when you get into into calculus. End behavior is one of those rules that it goes with the leading coefficient test, like they go like hand in hand. So I have to look at this first to kind of see where it's going. But the end behavior is where the tails on the very outside of the picture are going. So the tails on the outside. So for me, what I look for on the end behavior is I look at the highest degree item one more time. So I'm looking at the highest degree term, but this time I'm not looking at the leading coefficient, I'm not looking at the leading number. What I'm looking at is the actual power. That's what I'm looking for. So now we're kind of mixing these two together because they go hand in hand really, really nicely. If your power is even, which mine is, right? The power is even, then your tails, what I mean by tails, this graph, you know how they have like arrows? These are very flowing, continuous graphs. They're supposed to be continuous the whole time. The tails will end up going the same direction. So on this one, since I have an even power, do you agree that my power on this thing is an even number, it's 2? That means the tails on the outside are going literally the same direction. In my case, the outside tails are actually going up like that. Now I don't know where they are, but I know they're going up. Now what gives that away? What's the number out front? 2, positive, correct? So it's going towards positive infinity. That's how I know that. Even powers typically go towards positive infinity. Okay, that's how it works. If the number outside was negative, like a -2, these tails would be going down. Now, I don't know what's happening in the middle. I have no idea what's happening in this area yet. But I know that the outside walls are going to be going up and they're in the same direction. Make sense? If it's an odd power, so I'm looking at power, so if it was an odd power, like power 3, the tails would end up going the opposite direction. So opposite directions are, maybe one goes up and the other one would go down on the other side. So if it was like a cube root, okay, so you know, like x to the third, this is what your tails would look like. One would go up and the other one would go down. And if you were to put a negative number outside, they would flip over. That's the same with power 5, power 7, these are what they basically look like. That's how I can kind of tell right away when I start a problem what's going to happen. I can see that instantly. It's like a 2-second check when I start with a polynomial. I can immediately see that. All right, questions on the first 2 rules. They really go together. You have to kind of see them as one rule. Okay, now, there's a lot of stuff that we get into here. Luckily, you guys are only dealing with polynomials. You're not dealing with rational functions where they have fractions. That's something we're going to see later. It's like I think it's like section 2 or 3, like that we're after this, like 2 or 3 sections after. We start to look at what happens when there's fractions and you're dividing. All right, so we have end behavior done. Now, the next part. Now we're looking for is the X Intercepts. This rule will take us the longest. It is guaranteed, for some reason, this rule is one of the hardest rules we have to finish out through the whole problem. No joke. Like, especially if the polynomials are bigger. Like, a square term is kind of easy. We'll see that here in a second. But cube rules, 4th roots, 5th roots, there's little rules we're going to learn through this chapter, this section, or this chapter I should say, in chapter 2 that we're in, how to figure out what the X-intercepts are. There's always a fail-safe way, but there's different rules. Like number one, you can set up a table. You can set up a table, put a bunch of X numbers down, put a bunch of Y numbers, and you can kind of see if it's going to hit the X-axis because the numbers will go from like negative to positive. What I mean by that is like, let's say this is my function, right? It's the one we're going to draw. And you'd set up a table, you'd put a bunch of X numbers over here, so let's go like -4, -3, -2, -1, 0, 1, 2, 3. And what you look for is you look for any time, now that's not going to happen on this problem, but you're going to look for any chance that when you go through these numbers, it goes from like a negative number to a positive number. Because what happened here, at some point between here, it had to jump across the x-axis if you think about that. Because it went from like, now this isn't your real numbers, but it went from like 0,3 to, or 0, -3, sorry, 0, -3 to 1,4. At some point between these two dots, it had to hit the x-axis. So there had to be an x-intercept there. That is called the intermediate value theorem. Value theorem. The intermediate value theorem is the theorem that we use to actually help us with that. Is that it basically says that between any two numbers, there's always another number that can be evaluated. Because you always go to decimals. But what we use that for is that in between two numbers like that, like two y values, there's always a number that we can find in between them. Namely, we can find the 0 that's right in the middle of them. So at some point there was an x-intercept there, and we can kind of guess what that number would be. That's what we use. The book actually states this really, really well. Like in the book, like they show you why we use it. But just for me, I just want you to see the common sense way is we use a table and it jumps from negative to positive. Luckily, like the problems I'm giving you in this first section, like this is your starting point, I'm only giving you very, very easy problems. Things that we can handle right now. We don't have to do all this like crazy amount of work. But that's the first rule. Second rule, this is by far the easiest. You factor. We're going to factor this problem up. But again, you need to know the 5 rules for factoring. Right? We did this in the prerequisite chapter before we started this year. That was back in August and September. That the rules for factoring was common factors, difference of squares, trinomial, cube rule, grouping method. There's 5 rules there. And you have to know them all. No joke. You need to know them like really, really well to be able to handle that. Now, if you cannot factor your problem apart, then you're going to have to, like if it's a square term, like a quadratic like this, you might have to use the quadratic formula. Quadratic formula is that -b plus or minus square root thing. Okay, that formula that only works for quadratics. If you're in a cube root, we have a root theorem that eventually I might introduce this tomorrow, or not tomorrow, Monday. I might introduce this. This root theorem isn't found until later. It's called the rational root theorem. It's where you can find rationals. So it's for rational numbers only. Rationals are numbers that can be fractions, positive or negative numbers. So they can be decimals, but they can be written as fractions. So we have that root theorem. That theorem is the one that I was kind of warning you of. It takes a lot of work. Like it is an intense amount of like work that has to be done when we do those. Now to do that root theorem, we have to be able to divide polynomials. And I don't know if you've ever seen dividing polynomials before, and not with like writing them in fraction form. I'm talking like literally like the house method, like long division, if you've ever seen that. I don't know, raise your hand if you've ever had to do a problem like this.
Oh yeah, we did plenty of those. I mean, I don't remember how to do it, but we did.
You did that in algebra 2? Okay. That's in the middle of this. That takes a seriously long time to do, especially when you have really big polynomials. So it's not fun. There's shortcuts. There's called like synthetic division.
Yeah, synthetic.
So,
I like that
Is
one.
that the fun one where you
Is
put
it
the
in
thing
the
in the
box?
corner and the eye?
Okay, alright, so, okay, good. So, at least you've seen that before, because if I had to teach you that for the first time, that is a pain in the butt. I don't wanna have to be the first person that shows you that, but if I do, fine, and so be it, I'll at least walk you through it. But that's something like, when we get to this rational roots, we have to guess numbers. You literally guess numbers and you divide each one. That takes a while, a long while. So, that's something we'll look at. Okay, but those are like the basic rules that I use. Now, if there's anything between that, it basically falls back to the table, and we use intermediate values to figure out decimals, like irrational numbers. So that's the first one. Now, this one is factorable. So let's factor this thing out. So factoring, the 5 rules, common factors. Does that thing have a common factor? 2. Let's take it out. We're going to factor out the 2. So we factor out the 2, that's x squared plus 4x plus 3. And now we got to keep going because you have to factor this thing completely. So we factor that. Next, we can do the trinomial rule here. So it's 2 parentheses. They're going to be the same sign. They're going to be both pluses. We're going to break up the x and x. And now we have to break up the 3, go 3 and 1, and that does make the 4 in the middle. So there we go. So we factor this in completely. It doesn't go any further after that. And now what we can do here is we can figure out what makes each of these parentheses 0. We ignore the 2. The 2 doesn't really affect anything because it doesn't have a variable. What would solve this thing to make it 0?
-3.
-3? What would make this thing 0?
-1.
-1. That's why these are called the zeros or X intercepts or roots. It's what makes them 0. So, -3 and -1. So in my problem, -3, -1. And now I can get a sense for where this thing is going. If those are my only X intercepts, that makes sense with my tails for going up. And we have one more thing we have to do with this before I erase it. But it's what I'm thinking is that we're passing through it like here, and then it's going to turn around and kind of go up, so the tails will eventually go the same direction. Now, what I just said a little bit ago is called passing through. This is the next rule we do, which is one of the hardest rules. It's really a rule that the book says we mix with the X-intercepts. And no joke, it's one of those weird things you just have to get used to. It's called the Multiplicity Test. The Multiplicity Test is something you do on X-intercepts. It's after you're done factoring, and it only really applies to factoring, by the way. You can actually see multiplicity test work out if you're doing the rational root where you do long division or synthetic division. You can actually see it in there too. The book says it's used for factoring, but I can actually show you how it applies to this thing where you do long division. There's a quick way of doing it, but what you look at for the multiplicity test is you look at the parentheses after you factor, and you look at the powers that are on those parentheses. So like, what's the power that's on this parenthesis right here?
1.
It's 1. What's the power over here? 1. If they're, so maybe I should write this down. If the multiplicity test, I spelled that in my head. Multiplicity test, if you have an odd power on those parentheses, if you have an odd power, like we do, right? We have odd powers on both of these. You're going to pass through that X-intercept. So, we'll pass through the intercept. So in my case, I am going to pass through the -3, I will pass through -1, and that makes sense with the tails where they're going. If your power is even, it will bounce off of that intercept. So that means it will literally come up to that intercept and turn around without looking like it passes through it. So I'll give you an example back here in a second. We'll do another one. Okay, does everyone understand the rule? I'll give you the example of the odd. Like right now we have, or I'll give you an example of even. Right now I have an odd power, so we're passing through these. me start to set up the camera here. So. All right. So in our case, we have odd powers. So we are going to pass through those numbers, and it makes sense with the tails where they're ending up going. That I'm going to pass through here, and then I'm going to end up having to pass through the next one, and that's why the tails go. They keep going, and there's no other X intercepts, so that makes sense. The tails are starting and they're ending up going up as we go from left to right. But the next example, I'll have you with a multiplicity where there's even powers as well, so you can see that. All right, next. So we did the multiplicity test. Now we have to do the Y-intercepts. This is one of the last rules that we do. Back to here. We do the Y-intercept. Oh, there's another rule. Symmetry test. Okay, Y-intercepts. This rule is by far the easiest. No joke. This is the easiest step, other than leading coefficient and behavior, because that's just you look at it in 2 seconds, you figure out where the tails are going. The Y-intercept is you plug in zeros for all the x's. So let's go back to this problem. So for the Y-intercept, you're going to make all the x's zeros, because this is what a Y-intercept looks like by default. All the x's are zeros. So I'm going to plug in zeros here. So 2 times 0 squared, 8 times 0, plus 6. What number do you get? 6. Because everything else would be zeros, and you add that to 6. So I'm hitting 6. 1, 2, 3, 4, 5, 6. And again, why I'm hitting it there? I'm hitting the y-axis. It's called the y-intercept for a reason. And that makes sense with my multiplicity, where I'm passing through and where those tails are going. So my green arrows are not in the right locations, but we'll kind of move them to make it fit. So far we have pretty much the whole drawing. I can basically sketch this thing. There's only one test left that you're supposed to do, and it's called the Symmetry Test. But does everyone feel comfortable with the Y-intercept? It's real easy. Most people can do it in their head without even having to write anything down. They're like, okay, it's 6, because you put in all the zeros. All right, last one is called symmetry. Is this thing even, odd, or neither symmetric? That's what it is, okay? There's a test that we do for symmetry. So this is the last rule. Maybe you want to write a little, I ran into the space there, but maybe you want to write this. This is the symmetry test. Symmetry, if you don't know, things that are symmetric look balanced. They look like they're the exact same thing on one side to the other. It's like mirror images of each other. So for a symmetry test, there's one simple test that you do. You take your original function, and what you do is you plug in a negative x into the problem. So you're substituting in a negative x into this thing. And what happens when you do that, you look at the final answer, what happens after you simplify it with all the negative x's in there. So I'm going to plug mine in so you can see this. So I'm going to take this, I'm going to plug the negative x into all these x's. And if there's not an x, that just stays the same. So the 6 just stays, there's no x there. That's the first step. Now you have to use a little common sense when you square these or put them to any powers. If you square a negative x, what happens to it? Turns positive, right? Because putting anything to the power 2 makes it positive. So that'll be x squared, okay? When I have it to the power of 1, what happens to the negative? Stays, right? So the negative sign will actually come to the outside and make this a negative 8x. And then the 6 will stay the same. Now that we've simplified that down, just using common sense, even in odd powers, like what happens to the negative sign. Is this problem, is this exactly the original thing you started with? No, it's not, right? Because that 8 turned out to be negative. It's not the exact same thing you started with. So it's not an even symmetry type of problem. It's not even symmetric. So even symmetric is that when you plugged in the negative x into that problem, somehow it turned out to be just the original function again. It was like the original thing, it didn't even change anything. Because maybe everything had even powers on it. It's the one thing that I checked. Well, this doesn't have even powers. There was kind of a mixed bag of evens and odds, and this is an even power, so it's definitely not even symmetric, because it's not turning back to the original item. Is it odd symmetric? Odd symmetry, or odd symmetric, is when you plug in the negative x into your function, and it just turns out to be the exact opposite of what you started with. Is this thing exactly the opposite of the original problem? Like, is everything negative? No. No, it's not. It's not the exact opposite. So it's not odd. So this is not symmetric. What I mean by that is across the y-axis, I'm not having the same looking picture, right? This picture would be even symmetric. It's like perfectly balanced right and left. Odd symmetry would look like this, where they're doing the complete opposite thing here and here. Like one's going up, the other one's going down. I don't have that. You're actually seeing here, like this thing is doing some weird stuff over here, but across the y-axis, it's not doing the same thing. So I could actually tell by where the intercepts are, whether this thing is perfectly balanced across the y-axis. It's always the y-axis in the middle. That's how we're checking for symmetry. So it's not doing something like this where it's perfectly flowing. Something else is happening on this side that's different than that side. Now, why you'd ever need to know that is because sometimes when you're in a really big polynomial, it does a lot of like oscillations up and down. It has turning points. And you need to see, do I have another turning point? Like if this thing is supposed to be symmetric, maybe I have to make it look the same on the other side. So I have to like make sure the graphs do the same thing. So it's kind of like that little extra fill. Now that I've done all these steps, I can basically draw this thing. So this is what it should look like. It should look like this. It does some point where it turns around. I have no idea where this is. We're going to talk about that here in a second. It's going to come back up and pass through up here. This is what it should look like. Now, notice my little arrow. No idea where the little dot is. That's what we learn later. In fact, you probably already learned it now in Algebra 2. But it's one of the parts we talk about when we do conics. We'll talk about parabolas as part of the conic. Questions? Okay, now, if you actually go into a Chromebook and you actually type this in Desmos, I'll save you the time, I'll type it for you. So if you actually go type this, we're looking at, does it look like that? That's what we're looking for. The only problem is we don't have this little turning point. I have no idea if this is higher or lower. That's something we'll look at later when we figure out on a quadratic especially, we can figure out where that origin point is, like the center. Okay, on the last test we just did, the differential quotient, problem number 5. Remember that one with the f of x plus h minus f of x, that huge thing you had to simplify? That problem, what you were doing there, tells you where to find that little dot. That's what we do in calc. Because on a really big problem, where if it does a lot of ups and downs, right? You know, on a really big polynomial, that differential quotient will tell you every spot where it hit. That's what it's good for. And that's what a lot of people don't know. That's why I was kind of feeling like you're seeing the gaps, how they all fit together, but you won't actually do that until Calc 1, because that takes a while. Especially on a really big polynomial. You guys have to do really small ones. Okay, well let's type this in so you can see this. This is what I'm predicting. Okay, does everyone have that image in their head, what it looks like? Okay, all right, let's graph this thing, and this will be my last problem today. We're not going to do another one. We'll save it, because I want to give you some time to read it. So if you want to get your homework, you can do that. I'm going to pull this up on a graph just so you can see this. I think it is important that you get to see how to graph this thing. Again, you can type this in Desmos the same exact way. All right. Okay, I'm going to type in my function. What is that? 2x squared. And what is it? Plus 8x. Plus 6. There it is. Now let's zoom out a little bit. And you are seeing that it is hitting that. It is hitting 6. It is hitting -3 and -1. And this spot down here is that turning point. So it's almost exactly what I was kind of showing you. The problem is this spot right here is something we'll learn in the later sections when we get back to polynomials and refresh your memory on how to do quadratic formulas and factor those things, get to the standard form. But also the differential quotient, something I will show you eventually, what you can do with that thing. All right, but that's it for today. The rest of the time is yours. You have about 7, 8 minutes. 7, 8 minutes here. You can kind of work on your homework. Homework's due Monday. If you're done, you can work tomorrow. Yes. We can go fast though, so they know you're coming home from class. We got an email that will follow the email, so they know you're more consistent on the class.
So we're so I don't read about it.
Or is it due like every night?
Kill, did you finish that?
Like the kids?
What?
I would don't know.
No, I didn't.
I should probably just buy it.
Yeah.
That's,
Finish your class.
but I don't know if they're. But yeah,
We
you
can help
probably.
like offset with it.
So I can
So I can see like the process.
If you're done with the homework, you can work on it wherever you need to, and a lot of you already got the homework done the other day.